Okay, hello everybody. My name is Raphael Ebenhock. I'm from Stuttgart, Germany. And within the scope of my thesis, I developed a numerical model which predicts the flow through a wind farm. To get an impression what my model does, I illustrated here some calculated velocity fields. Here you can see a top view on the wind farm, and here on the left you can see a cut through this wind farm. But now let's just focus on here the streamwise velocity component. You can see here the flow comes from this direction and then gets decelerated along the wind farm due to the fact that the wind turbines extract kinetic energy from the inflow. This last turbine, there's an energy loss due to the wake effect. And you can see here my motivation for the thesis. First, as we saw already today, that the wind power is the fastest growing source of renewable energy. However, there are economic, social and environmental constraints which force the wind farm planners to cluster their wind farm in large area with a real dense turbine spacing, which then of course increases the wake effect inside the wind farm. At the same time, by using the state-of-the-art wake models, we have huge uncertainty during this energy yield assessment. A second point is that there's really a clash or conflict between here the complex flow behavior of with various parameters on the reality, and then on the other side the industrial demands. The industry wants to an accurate real-time simulation of executed on a personal computer. You can see here that a new generation of fast and reasonable accurate wake models is strongly needed. Now to the milestones of my thesis. First step was the development of the 3D model. Simplified, you can say that the approaching flow here faces a wind farm and then gets decelerated by small perturbation quantities due to the distributed body forces here. I linearized the Reynolds average Navier-Stokes equations around the incoming base flow by assuming that the perturbation quantities are much smaller in order of magnitude compared to the inflow velocity. In the next step, I validated my model against measurements conducted at KTH wind tunnels and also provided by Vattenfall. Here an exemplary result quantifying the so-called global upstream blockage effect. And this effect is very important, but it could, for example, not be described by the current wake models as the Jensen model, for example, simply because this model cannot account for the region in front of the wind farm. As you could see, the demand for a model like the proposed one is currently quite high, since the model really addresses the shortcoming of the wake models currently used in industry. It uses an innovative approach to calculate the wake-induced losses for an entire wind farm. You can see here some other models which are just capable of calculating the velocity field for a few turbines or single turbine cases. And it's not based on empirically estimated coefficients or predefined models like these ones. These are the widely spread industrial wake models. It uses a very good numerical scheme compared to also the direct competitors. And as I explained in the previous slide, the linear approach makes it much faster compared to conventional CFD models. So to sum up, you can say that the developed model has the potential to improve the industrial wake models in terms of accuracy or the physical mechanisms behind it, and also regarding the computational costs or the CPU time needed to calculate the fields. Thank you for your attendance.